They called it a weed. Governments banned it. Agricultural extension offices issued warnings, and it grows without a single drop of irrigation, multiplies underground every season, survives drought that kills wheat, and feeds communities when centralized food systems collapse. The sunchoke was reclassified from survival technology to invasive threat the moment industrial agriculture decided which plants deserved to exist. What was once cultivated across 3 continents as famine insurance is now legally restricted in multiple states, removed from seed catalogs and erased from agricultural memory. This is not about a forgotten vegetable. This is about how economic systems rewrite survival itself. Before European contact, the Great Plains tribes cultivated Helianthus tuberosus in systematic patches near winter encampments. Archaeological evidence from pre-Columbian sites in the Ohio River Valley shows concentrated deposits of sunchoke tubers in storage pits dated to 900 CE, alongside evidence of intentional propagation. These were not wild harvests. They were managed perennial systems. The tubers were planted once and produced for decades without replanting, without irrigation infrastructure, and without soil amendments. French explorers in the early 1600s documented native communities in the northeast, relying on sunchoke patches as guaranteed food sources during late winter when stored corn ran low. Samuel de Champlain recorded in 1605 that indigenous groups near Cape Cod directed settlers to existing sunchoke fields, explaining they required no maintenance and produced even when other crops failed. By the mid-1600s, French colonists in Quebec and Acadia had adopted the crop as a hedge against wheat failures, planting it along field margins and in areas too dry for European grains. Colonial records from New France show sunchokes listed in provisioning inventories for remote trading posts, specifically because they required no resupply and no cultivation labor. Russian peasant communities in the Volga region adopted the crop in the 18th century after it spread through Eastern Europe. By the 1800s, it was documented in rural household gardens across regions where grain harvests were unstable. This was not cuisine. This was architecture for surviving system failure. The survival technology is in the biology. Sunchoke tubers remain viable underground through winter freezes, can be harvested throughout the cold season without storage infrastructure, and regenerate from fragments left in the soil. A single tuber planted in spring produces 10 to 20 tubers by fall with zero water input beyond rainfall. The plant's root system reaches depths of 6 to 10 feet, accessing moisture unavailable to shallow-rooted annuals. During the Dust Bowl, sunchokes continued producing in abandoned fields where wheat had failed for 3 consecutive seasons. The USDA documented this in internal reports from 1934, but never promoted it as a drought mitigation strategy. The plant tolerates poor soil, requires no fertilizer, and spreads vegetatively, meaning no seed supply chain. Once established, a patch produces indefinitely. The French colonial strategy was to plant it once near settlements and treat it as permanent infrastructure, comparable to a well. In Russian peasant systems, households maintained sunchoke patches as insurance, harvesting only during grain shortages. The system was passive resilience. It required no activation until needed, and it could not be disrupted by market failures or supply chain collapse because it existed outside those systems entirely. The Russian famine of 1891 to 1892 killed between 375,000 and 400,000 people, primarily in grain-dependent regions. Provinces that had adopted sunchokes as part of household food security showed statistically significant survival advantages. Zemstvo records from Samara and Saratov provinces document that villages with established sunchoke cultivation reported 40 to 60% lower mortality rates compared to villages relying entirely on rye and wheat. The difference was not marginal. It was the difference between community survival and demographic collapse. The tubers were harvested directly from frozen ground throughout the winter, providing calories and nutrients when grain stores were exhausted. Medical reports from the period noted lower incidence of scurvy in regions where sunchokes supplemented diets due to the tuber's vitamin C content, which remains stable in raw form. This was not folklore. This was documented, repeatable, and ignored in subsequent agricultural policy. When the Soviet collectivization campaigns began in the 1920s, sunchokes were excluded from state planning because they could not be centrally controlled, mechanically harvested at scale, or stored in state facilities. The crop that had saved villages in 1891 was systematically removed from the landscape because it was incompatible with centralized agriculture. A single acre of industrial corn requires approximately 600,000 gallons of water per growing season in modern irrigation systems. An acre of sunchokes requires zero irrigation and produces comparable caloric yield. Corn demands synthetic nitrogen fertilizers derived from natural gas, with an average application of 140 pounds of nitrogen per acre. Sunchokes require no fertilizer and actually improve soil nitrogen through microbial associations. Industrial corn is an annual monoculture replanted every year with purchased seed, requiring diesel, machinery, and supply chain stability. Sunchokes are perennial, replant themselves, and operate outside industrial input systems. A single mature sunchoke plant produces 8 to 12 pounds of tubers. At standard spacing, an acre yields between 8,000 and 12,000 pounds of edible tubers with zero inputs. Modern corn yields approximately 180 bushels per acre, translating to roughly 10,000 pounds of grain, but that output depends on continuous industrial support. In collapse conditions, corn yields drop to near zero within one season. Sunchoke yields remain stable because the system does not depend on external inputs. The USDA tracked these comparisons internally during the Cold War as part of civil defense food security research, but never translated findings into public agriculture policy. Modern nutritional analysis confirms what historical communities understood empirically. Sunchokes contain 75 calories per 100 grams, with 17 grams of carbohydrates primarily in the form of inulin, a prebiotic fiber that does not spike blood glucose. They provide potassium, iron, and thiamine in concentrations comparable to potatoes, but without requiring the water or soil quality potatoes demand. Research published in the Journal of Agricultural and Food Chemistry in 2003 identified sunchokes as one of the highest natural sources of inulin, which feeds beneficial gut bacteria and improves mineral absorption. Studies from the University of Manitoba in 1998 demonstrated that sunchokes grown in degraded low-nutrient soils produce tubers with nutrient profiles comparable to those grown in rich agricultural land, a characteristic almost unheard of in cultivated crops. The plant's deep root system allows it to access trace minerals from subsoil layers that annual crops never reach. This explains why historical populations relying on sunchokes during famines showed better health outcomes than would be expected from a single crop diet. The plant was not just calories, it was a nutrient access technology that worked in conditions where conventional crops could not function. The economic structure that erased sunchokes from the food system was not a conspiracy. It was an alignment of incentives. Post-World War II agricultural subsidies in the United States were designed to maximize grain production for global export markets and industrial feedstock. Subsidies flowed to annual crops that required seed purchases, synthetic fertilizers, and mechanized harvesting, creating revenue streams for chemical companies, equipment manufacturers, and seed corporations. Perennial crops like sunchokes, which required no annual seed purchase and no chemical inputs, generated no secondary economic activity. Agricultural extension services, funded by these same industrial partnerships, began classifying sunchokes as invasive and problematic, citing their tendency to spread and their difficulty in mechanical harvest. State noxious weed lists added sunchokes in the 1970s and 1980s, not because they harmed ecosystems, but because they were economically incompatible with industrial agriculture. The language of control shifted from cultivation to eradication. Seed catalogs removed them. University agriculture programs stopped researching them. The USDA's germplasm preservation system maintains sunchoke genetic lines in cold storage, but does not promote them. The crop was not banned outright. It was smothered by an economic system that could not profit from it. This pattern repeats with mechanical consistency. Amaranth was a staple grain of Aztec civilization, capable of growing in arid conditions where maize struggled, and it was systematically suppressed by Spanish colonial authorities because it was associated with indigenous ritual and could not be controlled through encomienda labor systems. By the 20th century, it was reclassified as a weed in US. Agriculture, removed from grain markets and largely erased from Western diets. Perennial wheat varieties developed and used in Central Asian agricultural systems for millennia were abandoned in favor of annual hybrids that required replanting and purchased seed, despite their lower water requirements and higher resilience. The International Maize and Wheat Improvement Center maintains these genetics in research banks, but does not promote them for commercial agriculture. Culinary and agricultural knowledge is not lost accidentally. It is removed when it conflicts with economic models that depend on continuous input consumption. The systems that removed sunchokes from the food supply are the same systems now buckling under resource strain. Industrial agriculture depends on fossil water from aquifers that are depleting faster than they recharge. The Ogallala Aquifer, which supports grain production across 8 U.S. states, has lost 30% of its volume since 1950 and is projected to be functionally depleted in major agricultural zones within 30 years. Synthetic fertilizer production depends on natural gas, which is subject to price volatility and geopolitical disruption, as demonstrated by the 2021-2022 global fertilizer crisis that doubled costs and caused supply shortages across the developing world. Climate models project increased frequency of simultaneous breadbasket failures, where major grain-producing regions experience crop losses in the same season, a scenario that occurred in 2010 and contributed to the Arab Spring. In these conditions, the crops that were erased for being economically inconvenient become the only systems capable of functioning. Sunchokes do not care about fuel prices, supply chain delays, or aquifer levels. They grow in the margins, the abandoned fields, the places industrial agriculture has written off. When the systems designed for efficiency under ideal conditions encounter conditions that are no longer ideal, the technologies that were dismissed as primitive become the only ones still operating. The reclassification was never about biology, it was about control. A food system that functions without continuous external inputs is a food system that cannot be centralized, commodified, or regulated through supply chain leverage. Sunchokes represented a form of food security that existed outside economic dependency, which made them incompatible with a model that requires dependency to function. History does not erase knowledge randomly. It erases knowledge that threatens the systems writing the history. And when those systems fail, the knowledge that was erased is the only knowledge that still works. If this vault revealed something they tried to erase, subscribe to preserve what history tried to bury. Knowledge survives only when it is remembered. The next vault opens soon,